Okay, in the last video, I said go remind yourself what is the difference between an intensive property and an extensive property. So the intensive property, well, the extensive property, we'll start there, is dependent on how much mass is present. So the more mass I have, the more of the total energy that I'm going to have. I talked earlier about adding cold water to a system. Even though it's colder, it still has energy. So as I add mass of cold water in, it's adding total energy, capital E, to the system. However, the lowercase e, the energy per unit mass, um, that is not as that is scalable, right? So it doesn't matter if I've got water here at, let's say, 40 degrees inside my bottle of water here. It has the same energy per unit mass as if I fill this entire room full of the same kind of water at the same temperature. They're both going to have the same energy per unit mass. It's really just going to depend on what temperature that water is at. It's going to determine what energy per unit mass we have there. That's an intensive property. It's essentially scalable depending on how much mass is present. So again, the lowercase letter of a particular variable we're going to use to describe the intensive version of a property, right? The one that is per unit mass, the one that is scalable depending on how much mass is present. And so we'll see that multiple times throughout the semester, and then later courses like heat transfer, design of HVAC systems, whatever courses you may go on to take later on in the thermal sciences. Okay. All right. So today's focus, chapter 2 for us in the Chingle text is Introduction to the First Law. It's really all about energy, reminding us about types of energy we already know from Physics 1, and then expanding into additional types of energy that we've not encountered yet. So two of our friends from Physics 1 here are kinetic energy and potential energy. And so kinetic energy, of course, just like it was in Physics 1, that's mass times speed squared divided by 2. And if you want to look at what we call the intensive version of that, lowercase ke, which is capital Ke divided by mass, is just going to be speed squared divided by 2. Just like lowercase pe, the specific potential energy is just going to be G times H. Right? So again, that's a common thing we'll see is the lowercase version of a variable represents the one that is per unit mass. These are what we call macroscopic energies. Macroscopic energies. One of my favorite questions I like to ask a class, am I moving right now? And I'll pause and kind of stare at you blank with a blank stare and blink a little bit until I get an answer I like. Am I moving right now? And the correct answer here is actually a question. Correct answer is a question. Relative to what? Relative to what? Am I moving right now? Well, relative to what? How are you being measured? Because relative to the sun, we're moving very, very fast, right? Very, very fast, in fact. Relative to the camera right now, I'm really not moving at all. So it just depends on what is your frame of reference. For potential energy, we're going to measure that relative to the center of the Earth. For kinetic energy, we're going to measure it relative to some point on the surface of the Earth. We're essentially assuming it's inertial. It's not moving. We're not considering the fact that it's screaming around the sun and screaming around the center of the Milky Way and wherever that is relative to the center of the universe. We're not so worried about it. We're going to consider the surface of the Earth is our frame of reference. And we don't have to worry about relative velocity at all in this class or relative motion in this class. I'll leave that for dynamics and other classes than for you later. Okay. But these are macroscopic energies. These depend on an outside reference for measurement, as opposed to microscopic energy, which is only dependent on the molecular structure and the molecular activity within our system. So you have internal energy of a system, that's capital U. That is the sum of all of the microscopic energies. And then how I would draw specific internal energy, that's lowercase u. I have learned over the years to put kind of hats on my uppercase U. I try to do that. I'm not perfect at doing it. That way, you know it's a capital U. It makes it a little more obvious. My lowercase u kind of looks like a lowercase v, but it has a tail on it. And this probably is a good opportunity for me to go through and talk about, kind of give you, add to your cheat sheet, your Steve cheat sheet real quick here. So what is this? Lecture 3. This is page 1 of something. You can call it your Steve cheat sheet if you like. Maybe you're adding things to it. How I draw a kilogram, for example, and pound. Right? So these are things we've maybe already have. It's like, what the heck is this, that scribble that he's drawing? What does that mean? Another one is, in fact, I'm just gonna set this aside. This is not gonna be a page from lecture 3. So we've already talked about total volume, right? Total volume. We've mentioned this last time. This is how I will draw a density. That's my lowercase rho. Density is mass per unit volume. We've introduced previously specific volume. So we've already introduced to you this concept of taking a capital variable, dividing by mass, and representing it with the lowercase variable. That is a very common thing, as I've said several times now. That's a common thing that we will use throughout the semester. You'll use in later thermal science courses as well. That is specific volume. Now we've introduced total internal energy, capital U. Lowercase u, when I draw a lowercase u, I put a tail on it because otherwise it can look an awful lot like my lowercase v. So that's normally how I draw my lowercase v. You need have some way of knowing the difference between a u and a v and a capital V and a capital U. This is how I do it. All right, this is specific internal energy. Specific internal energy, which is, of course, capital U per unit mass. Now, we are going to use the letter V for 3 things throughout the entire semester, and they will actually show up in the same equation in just a minute. This is speed, or the magnitude of velocity. Just like in physics, we'll use capital V to represent speed. Now, that means you need to have some way of knowing the difference between, are you talking about volume or speed? This is how I do it. I cross my V if it's representing volume. I don't cross it if it's representing speed, but I use a capital letter in both cases. How do you know capital from lowercase? I try to exaggerate and make my lowercase much smaller, but I tend to not put a really crisp corner in the bottom. I try to be a very crisp corner in the bottom of my capital V and not so crisp in my lowercase v. I'm pretty consistent about that. I'm not perfect, but that's, if you're looking at it, is that a lowercase v or a capital V? That's how I differentiate between the two. If you look in the textbook, they'll have a different font case, a different typeface font that they're going to use to represent the total volume than what they will the specific volume. Some text will put a cross through it, but whatever you do, you need some way that you know, are you talking about volume, specific volume, or speed? Because again, we're going to see in just a second here, all 3 can show up in the exact same equation. So you've been warned. Have some way of knowing the difference. This is my Steve's cheat sheet. I'll set this aside and keep this handy for us throughout the semester. Okay. So we are talking about microscopic energy, specifically the internal energy. The internal energy is all of the microscopic energy within a system. So again, I've got my bottle of water here. And those molecules are in there. They're rotating and they're spinning and they're vibrating. They're doing things. And they have a particular phase, right? In this case, they're in the liquid phase. So how do we determine this U value, this total internal energy? Well, I need to take my scanning electron microscope and then go in there and actually look at each of the individual water molecules and measure their speed, measure their rotation, and add up all of those energies represented by those quantities, and that becomes my internal energy. And that is ludicrous. We do not have the tools of the technology to do that. We're just now getting to where we can begin to see atoms using different microscopy techniques. No, what we're going to do is we're going to estimate the internal energy based off of especially temperature, not temperature alone, but especially temperature and the phase and then other properties. And that's going to be really our focus of chapter 3 is how do we estimate what the internal energy, what is the microscopic energy of the molecules within a system based on things that we can measure because we have multiple ways of measuring temperature and volume and pressure. We talked recently about the manometer, and that's a very low-tech, simple way of measuring pressure, but we will base our estimates for the U value, off of things that we can measure. So we have all of these types of energy that we've just talked about here, right? These are what we call the energy of a system, right? These are the energies of a system. All the energies of a system. I can have internal energy, I can have kinetic energy, and I can have potential energy. So that's capital U, mv squared over 2, mgz, or mgh, either one's fine. But in this case, we're talking about elevation. That's z value. We talked about that last time. So these are the energies of a system. And if I divide those per unit mass, you see we're using now the lowercase version of each of these variables. Okay, so this is internal energy per unit mass and kinetic energy per unit mass and potential energy per unit mass. So these are the energies my system can have. Okay, so 3 types of energy there. Now, something else we need to introduce here is this idea of the dot above a variable. M dot. M dot, that's M with a dot above it. Right? M dot. I should put quotations there. And I'm going to do that while I talk a little bit. So M dot represents the mass flow rate. That represents the mass per unit time. M dot is equal to mass per unit time. If I have a control volume, I might want to know how fast mass is flowing through it, either into or out of that system. So I need to be able to measure the rate at which mass is flowing through. Now, if I put V with a dot above it, that is, again, we read that V dot. That is volume per time. V dot, it represents the rate at which volume is flowing through a system. Now, if I know my mass per unit volume, that is density, so this is mass per volume, and here I have volume per unit time, that's V dot. So if I take mass per volume, and I'm just going to go to the document camera and write this out. So if I take density times V dot, that's going to give me M dot. Right? So again, M dot being mass per time. And if we just do a dimensional analysis, this makes sense, right? Density being mass per volume. V dot being volume per unit time. That's what these represent. Okay, you can see a catapult here for a physics exam on the back of this. I apologize. All right, I'm going to wrap this video up real quick. But again, if we just do dimensional analysis, you can see that if I take m dot, multiply that, or I can say that is the product of rho times v dot, right? Mass per volume times volume per time gives me mass per time. Now I can go a step further with this, and I can say, well, if I have A, which is length squared, that's area, and notice that volume, of course, is length cubed per time. So if I take area, which is length squared, and I take speed, which is length per time, notice what happens just dimensionally. If I take area times speed, that gives me length cubed per unit time. This is v dot. The area times the speed, if I have some sort of a conduit here, I have fluid flowing out of it, and that fluid is coming out at a particular speed, and I can find the area, the cross-sectional area of the conduit of that pipe. If it's circular, that's just the area of the circle, pi r squared or pi d squared over 4. So find the area of that cross-section times the speed. The product of area times speed gives me a volume per time. That's the volumetric flow rate. So let's say I had a garden hose or a pipe or something like that, and I've got water coming out of it. How would I measure V dot? Well, I always joke and say, well, I could sit here with a measuring cup and catch this water coming out with a stopwatch and figure out how long it takes to fill up, a 2-cup measuring cup. How many seconds does it take? And then calculate that back to some number of gallons per minute or cubic meters per second, whatever it is you want. But that might work. It's kind of weird, but it might work okay with water. It's not going to work very good with like molten aluminum, for example, or toxic ammonia refrigerant. That's not going to work. I need some way of measuring V dot, volume per time. So how I do that is if I know a cross-sectional area and I have some meter, some electronic device that measures the average speed through some other properties of the fluid flowing through it, if I can find the speed and flow it through a known cross-sectional area, that product gives me volume per time. Knowing the density of the fluid, that gives me mass per unit time. All right, I'm going to stop there. I've gone a little over, and that's where I'm going to pick up the next video.